Okay, let's start with a typical AP question. No calculators on this question right here. The question is, what is the limit as x approaches 5 of the function 2x squared minus 50 over x squared minus 15x plus 50? So please pause the video for a second, work this problem out on your own, and then if you get stuck or when you think you've got the answer, unpause the video and you'll find my explanation. So you can pretty much assume if they are giving you a question like this, that 5 is probably an issue. So I'm going to go ahead and jump to the factoring stage right here. So if I factor the numerator, I start by pulling out a GCF of 2. When I do that, I'm left with x squared minus 25. So you see I went ahead and kind of combined those two steps. It's x plus 5 times x minus 5. The bottom factors into x minus 5 times x minus 10. So the x minus 5's cancel. That's where the issue was. That's where the 5 was causing a problem. So now we can plug in 5 to the top and the bottom. Notice my limit notation disappeared because I have plugged in the value. I have evaluated the limit. And then it's just a matter of simplifying. You get 20 in the numerator, negative 5 in the denominator. So the answer is negative 4. Negative 4 is the answer. You'll notice that there are always going to be 4 answer choices on the AP Calculus exam. They're shifting. Some of the AP exams still have 5 answer choices, but Calculus does have 4 now. So it's a good thing and a bad thing. You have fewer distractions, but then they've also made some of the problems a little bit harder. So anyways, let's look at our next topic. Properties of limits to find limits of other functions. Now, there is a handout outline kind of sheet of this on the haiku page. If you want to print it out, it's going to make your note-taking time a little bit less because I've kind of already got the outline on there. You can just kind of fill in along with me. Okay, so we've already established some of these basic limits, these theorems for basic limits. B and C are real numbers, n is a positive integer. We already know that first limit. As x approaches c, when your function is a constant, then the answer is always that constant. Don't forget that, okay? It's very important. The second one, we've talked about it as well. When x approaches c and your function is x, then the answer is always what you are approaching. Similarly, there's kind of a power rule to this. When you raise x to the nth power, well, you're just plugging in c. The answer, the limit is going to be c to the nth power. So really quickly, let's use these in real life. We've already done some of these examples, so this should be really easy. The limit as x approaches negative 5 of 11 is 11. Constant, answer is always the constant. The limit as x approaches 4 of x, very easy. It's just the value that you are approaching. The last one, almost just as easy. We just need to plug in the negative 3. Now, they do expect you to know these powers without a calculator. So think about it for a second. 3 squared is 9. So 9 times 3 is 27. 27 times 3, if you have to come over here and do it to the side, don't be embarrassed because I have to do it right now because it's just not coming to me. 81. And a negative number to an even power is always positive. So that is positive 81. If that were negative 3 cubed, that answer would be negative 27. Okay? So, let's keep going. Those are the easy ones. Here are some properties. We're going to kind of combine some things. So we've got B and C as real numbers again. N is still a positive integer. We have 2 different functions, f of x and g of x. They are different functions. And they have told us that as x approaches c of f of x, the limit is L. And as x approaches c, the same value of g of x, the limit is some other number, k. So here are some properties. If we have a scalar multiple, okay, so look here, we've got the limit as x approaches c of little b times f of x. We're just multiplying the f of x function by that little b. So the limit, we don't need to know anything else about the function f of x other than the fact that as we approach c, its limit is L, so the limit of b times f of x is going to be b times the limit of f of x. Okay? Some of these are going to seem kind of duh, but people still tend to overlook them. If we have a sum or a difference, if we're adding the two functions together, f of x and g of x, we're adding them together, we just add their limits together. And if we're subtracting them, then we subtract their limits. Okay, so depending on whether it's a sum or a difference, it's either going to be the limit of f plus the limit of k, or excuse me, the limit of f plus the limit of g, or the limit of f minus the limit of g. Product, same thing. If we're multiplying f of x and g of x, then the limit is going to be the product of their limits. Same thing for a quotient. If we're dividing them, it's the division of their limits, as long as k is not 0. If the limit of g of x is 0, then that's not going to work. You're going to end up undefined. But otherwise, it's just L over k. And this last one, the power, is kind of like the first, the simple one. If f of x is being raised to the nth, then you just raise its limit to the nth power, whatever power that may be, second, third, fifth, 10th, you just raise it to that power. Now, this one is not on your outline sheet, so you may need to take a minute to write it down. Composite functions, okay, remember doing f of g of x and g of f of x and stuff like that in pre-calculus. That's what this is going to talk about right here. So, say that the limit as we approach c of g of x is L. We're kind of switching things up a little bit. And the limit as x approaches L of f of x equals f of L. Okay, we're just plugging L into the function. Not anything new that we've done here. Okay, then the limit as we approach c of the composition, f of g of x. So we're plugging g of x into f. What you do is you start on the inside, just like you do with the composition of the functions. If I asked you what's f of g of 2, you plug 2 into g, you get that answer, you plug that answer into f. Well, same thing's going to happen here. We start with the limit of g of x, which was L right up here. So that goes right there. And so then it's just f of L. That's all there is to it. Okay? That's all there is to it. So we'll look at an example of that here in a second. In general, here's another general statement. If a function, f of x, is continuous at some c, we kind of already talked about this the other day. If it's continuous, as long as it's continuous at that point, then the limit as you approach that point is just the value of the function at that point. You plug c into the function. Simple as that. So, simple example, I've got f of x is equal to 3x squared plus 5x minus 6. I want to know the limit as I approach negative 2 of this function. I'm simply plugging negative 2 into my function and evaluating. Notice my limit notation is not there because I'm plugging in the negative 2, and I left the negative off right there. That would have caused problems. 3 times negative 2 squared is positive 4. Be careful with that. 5 times negative 2 is negative 10. So we've got 12 minus 10 minus 6. So 12 minus 10 is 2. 2 minus 6 is negative 8. And you can confirm that with your calculator, but again, trying to do as much as possible without our calculators here. Moving right along, here's where these come into play. You may say, well, okay, so what? If I've got the functions, I can just add the functions together and plug in the value. They don't always give you the functions. They love these questions where all they give you is one piece of information. All they tell you is that the limit as x approaches 6 of f of x is 4. That's all you know. You don't know anything about f of x. You don't know whether it's a linear function. You don't know whether it's a quadratic function. You don't know whether it's a rational function. All you know that as you're approaching 6, the limit of the function is 4. You don't even know if f of 6 is 4, but you know that the limit is 4. Okay, so let's use those rules that we were just looking at to find these limits of some manipulations of our function. Okay, so if we're squaring f of x, then we square the limit. So that answer to example A is 16. Example B, the limit as we approach 6 of 1 over f of x. This is just like a quotient problem, okay? We don't have another function that we're combining it with, so it's just 1 over the limit of f of x. It's 1 over 4. Okay, let's look at C. Be careful with C. This is a product rule because we are multiplying x times this square root of f of x. So the limit, I'm going to break it up. I'm going to write it like this so you can see what I'm talking about. This is the quotient rule. I can break up the limits like so. So what's our property? When the limit is approaching 6 of x, it's just 6. The limit as we approach 6 of the square root of f of x, we can apply that square root. Square roots are like powers. Remember, the square root can be rewritten as the 1/2 power, so we can apply the power rule here. So it's just the square root of the limit, which is 4. So we've got 6 times 2. This limit is 12. Okay? Feel free to go back, rewind, look over any of those that were a little unclear, but it really is just that cut and dry. Let's look at an example where we've got two functions that are interacting with one another. Example A is an example of our quotient or of our product rule. Again, okay, f times g. So we're just going to, we make sure, you got to make sure that this number matches the number that we're approaching in the given information. They didn't try to trick us here. I have seen that before. I have seen them try and trick you. So you got to be careful, make sure they match. But we're just going to multiply the limits. 3 times 1, so this one is still 3. B is a combination of the scalar multiple and the sum rule. We're multiplying our two functions by two different constants, and then we're adding them together. So it really is just 2 times the limit of f plus 3 times the limit of g. So 2 times 3 is 6, 3 times 1 is 3, 6 plus 3 is 9. Okay. C is like the example C from example 2, but it's a combination of the quotient rule here. So we've got the limit of g of x is 1. The bottom is x squared. Remember, we got to plug that number in right there. Don't be thrown off by that. You can just plug in the number. You should never, I think I'm safe in saying this, you should never end up with a variable in your answer for a limit right now. Okay? These should all have numbers. These should all have numbers. So this is 1 over 16. Don't forget, when you square a negative, it's always positive. That'll get you. Okay? And D is a little bit of a combination of them all. Okay? So we've got f of x, the limit of f of x is 3. Just keep that plus 1, because the limit as x approaches negative 4 of 1 is 1. Okay, break it all the way down. 3 times g, so the limit of g was 1, minus 9. So we've got 4 in the numerator, and 3 minus 9, so negative 6 in the denominator. Remember, I mentioned the other day, do not leave negatives in the denominator. Either put them in front of the entire fraction, or put them in the numerator. 4 and 6 are both divisible by 2, so when we divide both of those by 2, we end up with negative 2/3 as the final answer for the limit of that big problem there. Okay, so not very complicated. You just can't get distracted when they just throw in an x or an x squared or an extra constant or something in there. Okay, good. All right. Let's look at this example really quickly. Okay, I keep bringing these up because people keep on forgetting how to handle them. Here's your function. F of x is equal to x cubed minus 27 over x minus 3. The limit as x approaches 3 of f of x. Remember, if they're asking that question, 3 is most likely, not always, but most likely a problem. And we can see that it is. Okay, if we plug 3 into the numerator, 3 cubed minus 27, plug it into the denominator, we get 0 over 0. Okay, so indeterminate form, Indeterminate form, though, means that we can manipulate this to fix the problem. So, I haven't gotten rid of my limit yet. I haven't evaluated anything. I'm just rewriting. The numerator, that is the difference of perfect cubes. It may have been a little while since you factored this. So the cube root of x cubed is x. The cube root of 27 is 3. Now, we have another set of parentheses. We're going to put trinomial in here. It's built from the x and the 3 right there. We square the first term, so x squared is x squared. We multiply these two numbers together. X times 3 gives us 3x. And then the last is the last number squared. So 3 squared is 9. I teach SOAP. Use the same sign that was up here from what you were factoring. So that's a minus. Opposite. So it's positive in this case. And then the last sign is always positive. Okay, SOAP is same, opposite, always positive. Same, opposite, always positive. You will need, they expect you, I know they expect a lot out of you, and I expect a lot out of you as well. They expect you to remember all this stuff from way back when. So I will do my best to review it, but if I ever do something that you don't remember and I don't do enough of it, let me know so I can help you out with it. So the bottom, it's a linear term, so it can't be factored. So, but look at what happens. We've got x minus 3 in the top and bottom. That gets rid of our problem. So now we're looking at the limit as x approaches 3 of simply x squared plus 3x plus 9. No more denominator, no more issue. So we can just plug in and simplify. 3 squared is 9, 3 times 3 is 9, plus 9 at the end, 3 9s is 27. They expect you to do this without a calculator from beginning to end. Okay? All right. Let's keep going. Let's talk about something called the squeeze theorem. Okay, the squeeze theorem. Now, honestly, I have not seen this tested that much. There's one problem that they like to throw in there. What they use more is something that looks like the squeeze theorem, but it's not exactly the squeeze theorem. So you have to be very, very careful with these conditions. So the squeeze theorem involves 3 functions. We've got h of x, f of x, and g of x. Now notice, this is very specific. This is talking about the y values, okay? So the y values of this middle function of f of x are always between the y values of h of x and g of x. H of x is the smallest function here, g of x is the greatest function here. The y values for f of x are always in between, or they are equal to the y values of these other 2 functions. And it says for all x in an interval, okay? And here's the other condition. If the limit as x approaches c of h of x is L, which is the same as the limit as x approaches c of g of x. So that means at this c right here, h of x and g of x have the same limit. We're just going to call it L to keep it in general terms right now. What the squeeze theorem says is if these conditions are true, if your y values are in the middle and you got these limits going on that equal the same thing, then you know that the limit as x approaches c of f of x exists, and it's the same limit as the limit of the other functions. Now, I don't expect that to make sense with that explanation. Let's look at an illustration. All right, so here we go. We've got 3 functions here. We have h of x is the negative absolute value of x plus 4. Let's go ahead and graph that, okay? So y-intercept of 4, negative absolute value, it's facing down. So that's what we've got going on right here. Okay, there's h of x. Now I'm going to try and keep this color coordinated for us. F of x is x over 2 plus 4, which in other terms is 1/2 x plus 4. So it has the same y-intercept. So it goes through the y-axis at 4, and it has a slope of 1/2. So up 1 over 2, up 1 over 2, so forth and so on. And I am really bad at drawing straight lines, so please do not laugh at me here in a second. Try my best. Well, that one wasn't so bad. All right. And then finally, we have this other function, g of x is x squared plus 4. So it's a parabola. It also has a y-intercept of 4, but it's going to look like this. Yes, they expect you to know how to graph those three functions without touching your calculator, so you may need to brush up on those a little bit. So notice, let's look at our conditions. H of x, the blue function, is less than or equal to f of x, the green function, which is less than or equal to g of x, the purple function. Is that true everywhere? The blue function's always on the bottom, the green function's always in the middle, the purple function's always on top. So we have the first condition satisfied. Now let's look at the second condition. If the limit as we approach c, well, what's our c in this case? Let's look at the question. What is the limit as x approaches 0? So we need to know the limit as x approaches 0 of h of x. What is that? Well, as we approach 0 of h of x, the blue function, the absolute value function, we're approaching 4. Okay, and then we need to know the limit of g of x as we approach 0. G of x is the purple function, the parabola, the quadratic, whatever you want to call it. As we approach 0, we are approaching 4. So second second condition is met. So obviously we can see this with the graph. Okay, we can see that the limit of f of x as we approach 0 is 4, but I was looking at it, I was trying to show you, illustrate how the squeeze theorem can be applied here. Okay, so it is equal to 4, we can see that, we can do it algebraically, but I wanted you to see it from the squeeze theorem perspective, how the three functions line up and then the limits of the other two functions. Okay. But here's the key. These have to be the same value. Okay, these have to be the same value. I cannot stress that enough. They have to be exactly the same. Okay, let's use it. Let's get a little bit more interesting here. Let's use this to prove or find the limit as x approaches 0 of the sine of x over x. Now, we just talked about it a couple days ago. You should know that it's 1. You need to memorize that. But let's use the squeeze theorem to prove it, okay? So let's use the fact that they go ahead and set up, they tell us that the first condition is true. Cosine of x, that's our lower function. Okay, it is less than or equal to sine of theta over theta. That is the function of question. Okay, is less than or equal to 1. That's our upper function right there. They go ahead and tell us that that condition is met between negative pi over 2 and positive pi over 2. It's not true everywhere, but it is true between negative pi over 2 and pi over 2. And the value of question is within that interval. We're asking what's the limit as we approach 0. 0 is, of course, between negative pi over 2 and positive pi over 2. So our first condition is met. We need to see if the second condition is met. The limit as we approach 0 of our lower function, cosine of theta. Well, let's plug in 0 into cosine. That should be a 0, not a theta. What is the value of the cosine of 0? If you don't know that already, you need to be studying that unit circle. I will be giving you a quiz on that shortly. Okay, the cosine of 0 is 1. Now we need to know, well, how about that upper function? The limit as x approaches 0, the upper function is 1. How much more boring can you get than to be the function 1? Its limit is always 1. But that satisfies our second condition. The lower and the upper have the same limit, so that means the one in the middle has that same limit. Okay? The limit as x approaches 0 of sine of x over x is 1. Like I said, you got to memorize that. You got to know it. Got to know it, got to know it, got to know it. Speaking of what you got to know, we just talked about this one. Okay, it is equal to 1. Here's the other one you need to know. The limit as x approaches 0 of 1 minus cosine of x over x, it is equal to 0. Okay, it is equal to 0. Now, let me see if I can kind of help you logic your way through this one. Okay, let me see if I can help you logic through this. X is approaching 0. So let's pick a number that's really, really close to 0. 0.001, for example. Let's say x equals 0.001. Okay, so 1 minus the cosine of 0.001. Well, I don't know what the cosine of 001 is, and I'm not going to use my calculator to find it. I'm going to think through this, okay? I know that the value of cosine, as I get closer and closer to 0, as the angle is getting closer and closer to 0, the value of cosine is getting closer and closer to 1. So this number is almost 1. And then the bottom, we've got that x, 0.0001. Okay? So we've got 1 minus something that's almost 1, divided by a really, really, really small number. Okay? 1 minus something that's almost 1, divided by a really, really small number. So essentially, we have 0 on the top. 1 minus something that's almost 1 is 0. Okay? So that's one way to kind of logic your way through this, but the easiest thing is just to memorize these two limits. Okay? The limit as x approaches 0 of sine of x over x is 1. The limit as x approaches 0 of 1 minus cosine of x over x is 0. Just memorize them, put them on a flashcard, memorize them, memorize them, memorize them. Kind of something that I try and think through. We've got x over x in this problem. Now, there's nothing mathematical about this, but you got x over x, so that's kind of like 1. And then the 1 minus cosine of x, I just think about the cosine of 0 being 1, so 1 minus 1 is 0. Okay, cosine of 0 equals 1. So 1 minus 1 is 0. That's kind of how I think about that problem. Okay, if you're trying to come up with some way to remember it. Okay, let's find the limit here, okay, of tangent of x over x. We're actually going to use those two trig limits here in a second. So if we just plugged in 0, tangent of 0 over 0, well, we got 0 in the bottom, that's a problem. And if you think about the tangent of 0, guess what? It's also 0. So it's 0 over 0. But 0 over 0 is good. Indeterminate form means that we can do something to fix that problem. So let's turn tangent into terms of sine and cosine. If you don't remember this, you need to review that trig. Tangent is equal to sine of x over the cosine of x. Now, we now have a fraction within a fraction. I don't like that. So I'm going to put the x on the bottom over 1 so that I have a fraction over a fraction. And if I divide fractions, I keep the top one the same, and we flip the bottom one over, and it turns into multiplication. Now, guess what? Order of multiplication doesn't matter. So I'm going to rearrange this a little bit to make things a little bit more convenient. So instead of cosine of x being under sine, I'm going to move that x from the second denominator. I'm just going to slide it over. It's still in the denominator. That's perfectly legal. And I'm going to slide the cosine over to the other side. That's perfectly legal as well. They're still in the denominator. I just switched which fraction they were in. Now we can do that because it's multiplication. Do not do that if it's addition, but because it's multiplication, we can do that. All right, so now we got a product rule right here. The limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Well, we just learned this first limit right here. We memorized that it's 1. And guess what? I can plug 0 into my second one, and it's not a problem. because the cosine of 0 is 1. So I've got 1 times 1 over 1. Guess what? The limit as x approaches 0 of the tangent of x over x equals 1. Just like sine of x over x equals 1. So that kind of needs to go in your toolkit too. All right. So here are some strategies. They're there on your paper. Always, if you're trying to find a limit, try substituting in the value of x. First thing that you should always try. If possible, if that doesn't work, try and simplify the function. Then substitute the value of x. If you can't simplify, i.e. factoring, okay? Number 3, you need to do some algebraic manipulation. If you can't do any algebraic manipulation, then number 4, you need to try and rewrite the function as a combination of the functions you know the limits to. So that's kind of what we were doing with the tangent. We knew something about sine and cosine, so we rewrote tangent in terms of sine and cosine because we knew something about sines and cosines, so we could find that limit. Okay? So those are kind of your strategies that you need to follow when you run into these problems.